In this video, we first try to understand the generic contents that are available in the .lib file, and later we look into the process of improving our understanding in either writing our own .sdc file to cater for different design specification in our future, or modifying the existing attribute values for fine-tuning our constraints while discussing the generic contents of .sdc file. We will go through a brief superficial overview about the .sdc attributes that are used, and later we will look at the attributes and the values that are used in the constraint.sdc file. And the entire process is being reflected under this overview slide. The discussion that I am going to perform is based on the assumption that what a general .lib file would contain in it. This discussion might not be applicable to our standard cell library, as we have only 4 cells built using CMOS logic family. Whereas when you take a generic standard cell library, the library will generally contain many cells starting from a simple inverter cell to all the way to more complex cells like multipliers. Also, it not only have different logic functional cells, but also includes cells performing the same Boolean operation but differing in certain aspects. The figure shown here, as said, includes different cells performing different Boolean operations, as well as an inverter operation is being realized using different logic families and different drive strength. As you might know from your digital IC design theory, each type of logic family has its own merits in some aspect but fails in other aspects. Say for example, you have been given a constraint from a consumer that the design should use less area. For this, the obvious choice would be a pseudo NMOS inverter logic family. Similarly, for high speed, your choice would be a CMOS inverter with twice the drive strength. Now that you have got the general idea of the contents that are available inside the .lib file, I have also given you a hint about the choice of a particular cell even when multiple cells performs the same function. So we need a kind of mechanism to instruct the synthesizer to select a particular cell, and this mechanism is basically done through the .sdc file. So next we will look into the contents that are generally available inside a generic .sdc file, and later we will discuss about the attributes that are used in our .sdc file in a way to understand the meaning of each attribute. Basically, the .sdc files are written in Tcl format, and it defines constraints that helps the synthesizer to narrow down its choice out of many cells that performs the same function. One can actually classify the commands that are used in a general .sdc file into the following types. The first is the basic constraint commands that specifies the normalized unit values of different elements like resistors, time, etc. The next is the object access constraint commands that specifies how a particular cell instance in your netlist is selected. For instance, you want to apply a clock signal to all the cells that contains the port named as CK. Then you might use this object access constraint command to perform this. We will be using one of this command from object access constraint, which we will see in the later part of this video. The next comes the timing constraint commands, which is related to timing specification of the design. Say for instance, your design need to run at 100 MHz clock frequency, and you need to use one of this command to set it, such that it helps the synthesizer to pick the cell that fits this timing constraint and make the synthesizer to report about the time slacks. Next comes the environmental constraint, which actually sets up the environment that are necessary to perform the analysis, like timing analysis or an area analysis or even a crosstalk or EM analysis. We will be using some commands from this command set. The last type of constraint command, which is the multi-voltage command, which is widely used when working with multi-voltage domain. Now, with this basic classification of constraint commands, we will look at some of the commands that we will be using in our constraint.sdc file. But before that, we look at a basic theory of synchronous design, and later we associate commands to the synchronous systems, followed by which we look at their syntax and how different attributes of the commands can be used with visual representation. This is purely the theoretical part explaining about a synchronous system. As we know that in an RTL design, the data arrives in from a clocked device like a flip-flop and leaves the system again through a clocked device. Thus, the timing specification plays an important role in a synchronous system. Consider, for instance, that all the flops in this figure are operated with a clock that has a period of 20 nanosecond. So, within this 20 nanosecond, the data from the first flop should reach to its output Q, and then through the logic M and N, and finally to second flip-flop input before the setup time. In each stage, different delay parameters will be encountered in the path between the two flops, like clock to Q, and then the propagation delays, and then the setup time. Okay, so the general methodology to deal with this type of system is to first define the clock and then use this clock relatively to define the data and or the control signals. Now we will look into the commands superficially that plays a role in defining the synchronous system. As shown, the setup input delay defines the arrival time of the input data relative to the clock, whereas the create clock defines the waveform of the clock. The set clock skew defines the latency of a clock edge that it took for it to arrive at the input of a flop from a clock source, and this latency is primarily due to the parasitic wire delay. And finally, the set output delay defines the output timing requirement. Just to show you what is clock skew, here is a figure that explains the same concept that I discussed for set clock skew parameter. Sometimes you will also find commands that sets the uncertainty parameter that defines the uncertainty in the arrival of clock edges. This happens due to some supply noise or influence from some signals that run in parallel to the clock, or even the change in the ambient conditions like temperature would induce uncertainty in the clock signal. Now let's focus on create clock command, where the first switch specifies the period of the clock and the second switch specifies the duty cycle of the clock, and the final switch provides a name to the created clock signal. Note, this type of clock signal generation, where a name is used and not assigned to any clock ports of registers, we call it as virtual clock, and its main purpose is to specify the I/O signal timings of a combinational logics. So in short, it is used while synthesizing combinational circuits. Whereas the second example assigns the generated clock signal to the clock port of registers, and the register objects are accessed through this get port object access command. So thus, this type of syntax where the created clock is directly applied to the registers are used while synthesizing a sequential circuit. Next, we look at clock latency command, which specifies the additional delay that a clock signal encounters in a clock network. As shown in this figure, the clock latency has two components. One is the source latency, the other one is the network latency. The network latency, or the delay, is the time it takes for a clock signal to propagate from this clock definition point to register clock pin. Even the inversion of a clock signal, if it is present in the clock network, is taken into consideration when computing the clock network latency at the register clock pin. Also note that by default the clock latency command applies the delay to network latency delay, whereas clock source latency, which is also called insertion delay, is the time it takes for a clock signal to propagate from its actual ideal waveform origin to clock definition point in the design. It can be used to model the off-chip clock latency when a clock generation circuit is not part of the current design. As stated earlier, the clock latency by default applies only to network delay. So in order to apply a latency value for this source latency, you need to add a switch which is named as source. So in short, the source latency is the delay that we try to model outside the design under consideration, whereas the network latency is the delay encountered by a clock signal inside the design. Now we look at input delay command, whose actual physical representation is shown in this figure. The figure also depicts the different delay that a data signal encounters while it travels between two consecutive flops through the combinational network. These different delay parameters includes clock to Q delay, propagation delay through the combo logics M and N, and the setup time of the second flip-flop. Now the question is, at what time after the clock does the data input arrives to the logic that is inside the rectangular box? The answer is clock to Q delay of the flop plus the propagation delay of logic M. So this is the amount of delay that we have to specify as the input delay. Note here the value of clock to Q can be extracted from our .lib file since we have only one flop cell. But the question is how to know the propagation delay of this unknown M logic. Usually one can use a wire delay as an initial guess, and later, depending on the timing report, one can fine-tune the value that we are providing for the unknown logic M. Also note that this command and even the previous command that we discussed, which is set clock latency, actually emulates the environment that exists surrounding our logic circuit. Now let us look at an example to see how to define an input delay. As you could note that the rectangular box with the clock input encloses our logic that we wanted to get synthesized and optimized. The remaining logic shown here emulates the environment surrounding our logic. Note that the input to our logic can come from different paths, due to which one can use maximum path delay as well as the minimum path delay for the data, such that any path that the data comes from, it will fit within this range. And the same is reflected in the commands shown over here. As said, the value of input delay is summation of clock to Q, which in this example is 1.4 nanosecond, and the logic delay that is outside the design under consideration. As shown, we have two paths, one having a maximum path delay of 7 nanosecond, the other path having a minimum delay of 3 nanosecond, which when we add leads to two different values. And any input delay when an actual circuit that is placed outside our logic would induce an input delay that falls within the maximum and the minimum values. Next, we will look into another environmental command, which is output delay command. This command tries to emulate an output condition that our logic that is available inside this rectangular box would experience. Now the question is, how does the definition of output delay would impact our design that is available? One of the possible answer would be the choice of the driver strength that our logic is supposed to possess, such that it satisfies the timing constraint posed by the clock as well as the load the logic S would face. As shown, this output delay is defined as the summation of setup time of the flop that is outside our design plus the propagation delay of the logic T. As usual, one can use the wire delay as an initial guess to fit the value of propagation delay of logic T. Before we look into the actual command for the output delay, as a review, we will look into the definition of setup time and hold time. We know that the setup time is the time that the data signal should be made available and stable to the input of a flop before the active edge of the clock arrives to the flop clock input. Similarly, hold time is the time that the data should be made stable even after the clock edge. Note that this statement about this hold time is true only for a positive value of hold time. Now let's look at an example which requires a careful insight while defining the output delay than compared to the definition of our previous input delay command. Now, to illustrate the maximum output delay, consider that the out1 port changes its output value from 0 to 1. So this rising edge, when travels through this maximum propagation path, would reach the data input of the output flop after 14 nanosecond from the time the out1 port has created this rising edge. But based on the definition of setup time, we wanted this data to be available to the flop input well before the active edge of the clock by at least a setup time. Thus, considering these two requirements, that is the longest propagation path delay and the setup time, poses the output 1 port to have its output available by at least 14.8 nanosecond before the active edge of the output flop's clock signal arrives in. Similarly, the data at out1 port should be made stable, that is, to be held to a value of 1 even after surpassing the clock edge by 0.4 nanosecond, which is the condition imposed by the hold time requirement of the output flop. So, the data at out1 port needs to retain its value till somewhere around 13.6 nanosecond with respect to the active edge of the output flop's clock signal. Thus, the data at out1 port is not allowed to change throughout this entire 1.2 nanosecond, which when added to the longest path, that is 14 nanosecond, would place this requirement of this 1.2 nanosecond interval where the data is not allowed to change to 14.8 nanosecond to 13.6 nanosecond with respect to this active edge. A similar interval requirement of this 1.2 nanosecond can also be imposed for data that travels through this minimum propagation path. Again, this necessitates the data at out1 port to be made available before the active edge by a time value of about 4.8 nanosecond. After adding the propagation delay of 4 and the setup time of 0.8, also based on the requirement of hold time, you want the data not to get changed till 3.6 nanosecond from the active edge of the clock signal. Again, it creates a window of 1.2 nanosecond where the data is not allowed to change. Now, considering these two parts together, one can deduce that the data is allowed to change its value at out1 port well before 14.8 nanosecond from the active edge of the clock, which is basically derived from the maximum propagation path delay, and the data is not allowed to change at out1 port till 3.6 nanosecond with respect to the same edge of the clock signal, and this value is basically derived from the minimum propagation path delay. The same is reflected across the command 2 and 3 in this slide. Now it's time to look into the .sdc file contents. Since we are going to synthesize a full adder circuit in this experiment, which is a combinational circuit, we begin by defining a virtual clock whose sole purpose is to define the input and output delay settings in the environmental setup for timing analysis. So we are creating a clock signal with a period of 40 nanosecond and 50% duty cycle, creating a clock frequency of 25 MHz. Note that in the case of a sequential circuit design, we be using the command shown in this magenta color, where we are trying to use the object access command getPort to feed the clock signal to the flop circuits. Next is the clock latency command, which depends on the size of the logic through which it propagates. Based on the experience, if the circuit that we are working is small, then an initial value of 1 nanosecond can be provided, and if it is a large circuit, then one can pump up this value to somewhere around 3 nanosecond. In our case, since we are working with circuit that is too small, I'm setting it to 0.3 nanosecond. Next, the input-output delay setting. As we discussed earlier, we need to know the clock to Q data and the setup time data for the D flip-flop that we have characterized in our previous experiment. So now let us try to figure out these values in the next slide. Use the following command in your terminal to open up the index.html file, where you would find our cell DFFRN cell characterized data in the HTML format. As we know that to calculate the input delay, we need the information about clock to Q parameter of the sequential cell. Here the data are zoomed to show the values on which we are interested in. Clearly from the visual there are tables, and in each there are one row that corresponds to our requirement. As you could note that there are three values: minimum, average and maximum. We will consider the worst case situation and pick the maximum value. Thus in this case we have a clock to Q delay of approximately 0.82 nanosecond. We also know that we have to add an extra delay of wire, which in our case we choose an arbitrary value of 0.18 nanosecond, so that when we add both these values we end up having 1 nanosecond for the input delay parameter. Similarly, to calculate the output delay, we need the information about the setup time of the sequential cell, and this data can be found under the constraint table. Again, we pick the value that corresponds to the maximum, which in our case is approximately 0.07 nanosecond, and to this value we add somewhere around 0.03 nanosecond to get an output delay value of 0.1 nanosecond. The following SDC file has been modified accordingly, with 1 nanosecond for the input delay and 0.1 nanosecond for the output delay. The remaining commands are self-explanatory, and we will use them as it is for the entire experiment. Next, we will move on to our fourth objective, which is the methodology for synthesizing the combinational circuit design.